First, you can find the slides online at this address. You can also use the QR code. I really highly encourage you to either sit close or grab this link and follow along. There's a lot of code examples and compiler error messages. And I did test this out, and it's pretty readable in the front half of the room, but as you get further back, it can be a challenge. All right, anybody need me to leave this QR code up longer? All right. Otherwise, it's bit.ly/that-repo, that-repo. All right. And you can also check out the repo on GitHub if you want to see some of the example code that I use to produce a bunch of these error messages. That's a lot of what I'll be talking about is the Rust compiler error messages. I'd also like to thank MongoDB, which is my employer as of 6 weeks ago. They sent me here, and I will note that we are hiring. Last I checked, there was, I think, 80 engineering positions open, 29 of which were available remote in North America. There's remote in other parts of the world, and we have various offices. I don't think we have any Perl stuff. I'm doing Go at my day job. There is some Rust there as well, and C++ and other languages. So if you're interested in learning more about MongoDB, I'm happy to talk to you about it. I've only been there 6 weeks, so take it with a grain of salt, but so far I've really liked working there. All right. I do want to clarify, this isn't a Rust tutorial. I'm going to show a bunch of Rust code examples, but I'm not going to explain in detail like the Rust syntax or lots of detailed features of the language. It's more about, here's a bunch of features that people really like about the language and gives you a sense of the flavor, what it's like and what the benefits of using it are. But yeah, there's not a lot of low-level detail. I do encourage you, please do ask questions as I go. If there's something you find confusing, I'm happy to stop and kind of explain what some of the syntax is, but that's what the talk is, so just to be forewarned. So, in the 2021 Stack Overflow survey, which is probably hard to see the details of this image, Rust was the #1 most loved and least dreaded language. So in this graphic, blue is love, purple is dread. Rust was at the top. Perl was not in this top 6 list that I pulled. It was a little, sadly, further down, which it was below PHP, which I don't understand. But anyway, I still love Perl, but I also love Rust. And Rust was also the most loved from 2016 through 2020, and then yesterday they released the 2022 survey, and it was still the most loved. So people really, really love Rust. And just out of curiosity, how many people here have used Perl? Hands up. I'm guessing basically everyone. C, good chunk of you. C++. For you folks, Go. Okay. So especially the C and C++ people, you will really appreciate some of this. And I think actually if you've used Go, you might appreciate some of what Rust does. And if you use Perl, it's just a very different type of experience. So what's Rust? Besides, it's a programming language, obviously. It's often referred to as a systems language, but I put this in quotes because it can be used for a lot of things. So it can be used for embedded. That is a big space that Rust is used in. You can use it to write kernels. There's news that possibly the next version of the Linux kernel might include some Rust. People have been working on that for a while. But you can also use it to write like CLI programs. I've written a bunch of those in Rust. You can write games. There's people writing games in Rust, and you can even use it for front-end development. It compiles down to WASM, and you can run it in your browser, and I've done some of that myself. It's a compiled language. It's statically linked. Basically, everything is statically linked except libc, except if you want, you can statically link musl, so really have everything static. The compiler itself builds on top of the LLVM toolchain. It is type checked at compile time, so unlike Perl. It has a really powerful type system, and we'll see a bunch of examples of that, and that's one of the things that I personally really enjoy about Rust is the power and flexibility and kind of intelligence of the type system is really nice. It doesn't have any garbage collection, so unlike Go or Perl, there's no garbage collection, but it also doesn't have any memory malloc allocation that you do manually. So there's no malloc and no free calls, which is really cool. Most things go on the stack by default, but you can, if you want, control where things go. You can put things on the heap. You can even replace the global allocator, and there is work being done, I know, in the core to make it possible to kind of pass an allocator around to different things that allocate memory, so you can have even more fine-grained control over memory allocation. And you can also write code that doesn't allocate memory at all. Rust has kind of a split in the core libraries. There's core and standard. Core does not have any heap allocation. So if you only use that and you're in an environment with no heap, as is sometimes the case with embedded programming, you can just use the core library and have no memory allocations at all, or no heap allocations at all. I will show you. The short answer of how it frees memory is there's this lifetime and ownership system. It essentially tracks when a variable is no longer being used and it automatically frees the memory. But it's not garbage collection. It's not like a separate process. Yeah, it's closer to Perl, and it's like C if C would call free automatically for you when it no longer needed the memory. So my experience with Rust, I've written some CLI tools. There's a couple you can see on GitHub. One's called Precious. It's a kind of meta linter, meta tidier. It runs a bunch of linting and tidying programs for you. There's another one called UBI, the Universal Binary Installer. So basically, there's a lot of cool command line programs that get released as GitHub releases, and they're Go or Rust, so you can just download the single file binary. So this will do that for you, and just download the right one for your platform. And I actually started writing a music player as a kind of fun learning project. There's an importer that's a command line program, a gRPC backend, and a front end, in a web front end using a framework called Dioxys for Rust. The whole thing is in Rust, which was cool that I could do that. So why do people love it? Right when I was starting to work on this talk, there was a really handy Reddit thread on why Rust is so loved. And if you followed the link to the slides, you can click on this link and read it, maybe read it after I'm done. And there's a lot of stuff they mentioned, and it pretty much agreed with all the things I liked about Rust. So I'll go through pretty much everything that came up in the thread. So Rust's core proposition is that you can have memory safety and performance, which is kind of a pretty somewhat radical idea. If you look at the history of languages, you have high performance languages like C or C++, which are just, you know, great for producing seg faults and stack overflows and so on. Or you can have memory safety with languages like Perl or Python or Java, but you tend not to have that level of performance. Even a language like Go, there have been issues with, say, garbage collection performance and things like that. And Rust's core proposition is what you're not going to have the GC problems, but you're not going to have the seg faults, the stack overflows, the buffer overruns, and all that sort of stuff. And it kind of related to that, and kind of the same lifetime and ownership system I mentioned before also really helps with what they call fearless concurrency. There's a lot of concurrency bugs that are not really possible in Rust unless you use unsafe Rust. Same goes for memory safety. And there's this ownership of data is part of the type system. It has a lot of language features, really strong type system with things like ENUMS, traits, generics, and I'll go into more detail on some of these, pattern matching, all this cool stuff. The type system, however, does not have the challenges of pure functional programming. Nowhere in the docs have I seen the words monad, monoid, category, or arrow, which is great because I don't understand what any of that stuff means. I've tried to learn Haskell multiple times, and every time I get to the monads part, I'm just like, okay, my brain exploded, I give up. I think if I had to learn Haskell for work or something, I could probably do it. It's just, I can't get over that hump when I'm just trying to do it at home for fun. Has really nice tooling. There's a tool called Rust Up that gets Rust installed for you, keeps you up to date. Really amazing compiler errors. We'll see a bunch of those. The cargo command line tool, which manages both your dependencies, and those also how you build and run and test Rust code. Really nice tooling. Rust Analyzer is a great LSP server. Rust format, kind of like Go format, or Perl tidy. Clippy, which is a nice linter, kind of like Perl critic. And then people in this Reddit thread also mentioned the ecosystem, the community. It has pretty good documentation. I would actually compare it to Perl's, which I think Perl's core docs are pretty good. And Perl has a good culture of documentation, and I think Rust also has that. Of course, it's not perfect. There's lots of Perl modules with poor docs. There are Rust crates with poor docs as well. And then the ecosystem of modules, people particularly highlighted CERD and Rayon. CERD is serialize and deserialize. Rayon is a way to kind of very, very easily inject parallel computing into your Rust code base with almost no effort whatsoever. And then just the Rust community. The people found it very welcoming and friendly and supportive. And it's a place where, in my experience, the kind of bad behavior I've seen in other communities is generally not tolerated. There's pretty good moderation of various Rust spaces. And one of my personal favorites, there's not much good enough for me, but not for thee. By which I mean, almost every feature in the language is implemented in an open way where you can use those same features in your code. You can write things that act like just like all the stuff in the standard library. There's very, very few things that are implemented in the compiler itself. For example, you can implement overloading for most operators. You're holding up the done sign. Do you realize that, Felipe? I'm not done. Almost every core type is actually implemented in Rust, so you can go and see how it's done. You can do the same types of implementation for your own type. Most traits and macros are also implemented in Rust. Any type, for example, can implement iteration, which is really nice. Just not a lot of magic. And I compare that to Go, which is another language I have a lot of experience with, where all the cool stuff is in the compiler and you can't do any of it in your own code. And I find that very frustrating. So now I'm going to go through some various examples. So here's one example of memory safety. You cannot return pointers to the stack. So we're calling this function, returns pointer. It returns a reference to an unsigned 64-bit integer. We create that integer in the subroutine. It's put on the stack. We try to return a pointer, and Rust says, this returns a reference to data owned by the current function. It just won't let you do that. And there's some other types of error messages you might get if you try to do this a little differently, but the point is you just can't do this. It just won't let you return reference to local data. So you can't have that memory safety issue. There's no double freeze. As I mentioned, there's no single freeze because you don't have to free memory yourself. You can't really create pointers to freed memory. And again, this is all with safe Rust. Rust has this unsafe escape hatch. If you need to implement certain things, some of the core uses unsafe. If you're interfacing, say, with C or C++ libraries, you often have to use unsafe. But most of the time, you're writing safe Rust code. That's the default. You don't have to free memory. You don't have the possibility of pointers to freed memory. Rust frees the allocated memory when a thing goes out of scope, when nothing owns the data anymore. And all types can implement the drop trait, which is a lot like Perl's destroy. So if you implement drop, that drop method is called when your thing is being freed. Another example of memory safety and error prevention is you can't read and write to the same thing at once. So here we have a vec, which is an array, and we're going to iterate over the members of the vec through a pointer. We're going to try to push onto the vec at the same time. So we're reading, and then in the loop we're writing. And Rust says, cannot borrow vec is mutable because it's also borrowed as immutable. And I want to note that it actually tells you exactly where the immutable borrow happens and the mutable borrow happens, and it really gives you a lot of details. And this is one of the things I really enjoy, is these compiler error messages are just so nice. Like all these pointers, and they're in color. It's fantastic. I don't know how many of you have used Racco. It's the only other language I've seen that has this type of incredibly detailed, helpful, pretty compiler error messages. I mentioned fearless concurrency, so there's no data races. Here we have a hash map, and then we're spawning a bunch of threads, and what we're doing in each thread is we're saying, I want to get the entry for the key, named key, and if it doesn't exist, just insert a new entry with that key and a value of 1, and then I'm going to increment the value of that entry. So does anybody see what's going wrong here? You're laughing. Felipe, what's going wrong? Right, so there's a race condition here. We're trying to get a key, an entry for a key, or insert it, and then we're incrementing the value, and this is happening in multiple threads. They could all be doing this simultaneously, and for example, we could try to get the entry and then try to insert while some other thread is doing the same thing, or some other thread has already done that. It's just a disaster. But this code doesn't actually compile. It says, cannot borrow v as mutable more than once at a time. V was mutably borrowed in the previous iteration. So basically, when I made the first thread, I borrowed v mutably, and I can't borrow it again. And v, for reference, is the initial hash map that I made. So Rust just doesn't let me do it. So how can I do this? I make an arc of a mutex, and then I can use that. So an arc is an atomically reference counted wrapper. It basically is a way to share immutable data between threads safely. And then the mutex allows us to write to shared data in a safe way. So what we do is we clone the arc for each thread. The clone just makes a cheap copy. It increments the reference count at runtime. And then inside the thread, we have to call lock on the value. We can't read or write without the lock. And that's actually enforced by the type system. So the hash map itself is not accessible until we get the lock. And then when we have the lock, we can manipulate the hash map, and we know that we're the only thread doing that at the time, so the rest of this is safe. And then when LV, which is what we got from the lock, goes out of scope and nothing is owning it anymore, the drop method is called and the lock is released. And there's no way to forget to release the lock, and there's no way to have multiple threads get the lock at the same time. So the type system is enforcing our inability to have a data race in this code, which I think is pretty cool. Is the lock call a blocking call? I'm pretty sure it is, yes. And there are generally, for blocking things, there are like non-blocking variants. You can also do like async code that has blocking and non-blocking versions. There's a lot of possibilities. One of the downsides of Rust is there is a fair bit of complexity to deal with. There's a lot of different APIs. Because it's a powerful language and because it's aimed at allowing low-level code, they want to give you a lot of different APIs. So that is the downside. Yeah. Oh, okay, so the question is, what's the purpose of the unwrap? So we call v.lock.unwrap. And I'll explain more details later, but basically lock doesn't return a lock, it returns a result, which can be either the value you want, the lock, or an error. Unwrap just says, hey, give me the value or panic. It's not actually how you want to handle this condition necessarily, but for a short code example, it makes it easier to write. And I'll show exactly how you deal with those result values in a little bit. So I really like the type system in Rust. So we have enums. Here's a really simple example. We have 3 sizes, small, medium, large. And then we have this match construct. So if we match on a size, we can match against the enum values. This is a really trivial one. That derived bit at the top where it says derived debug partially, which I'm realizing is very hard to read. But this is why I wanted you to follow along with the slides on your own devices. That basically implements some traits for you, kind of like roles or interfaces. We'll go into that in a little more detail later, so don't worry about it too much. But what if we don't match every variant? What if we just match small and medium, but not large? Should this code seems like it has a problem, right? Like, what happens if we got a large? What is the code supposed to do? And in fact, Rust does not like that. It says non-exhaustive patterns, large is not covered. So it shows you the match where you did this. It shows the definition of size. It shows the definition of large. It even suggests that you fill in and match large and put a to-do. To-do will panic, I think, if you get to it, but at least you've satisfied the compiler. And so, again, I just love the compiler error messages. They're so nice. Now, enums can be more complicated than this. They can actually have values associated with them. So we make a struct, and then we have this enum of errors. The file error has a string. The size exceeded has an unsigned 64-bit integer. And the bad name has a named struct that it contains. So you can actually unwrap this stuff from the enums as part of matching and in various other ways. Any questions so far? Are we good? All right. I want to talk about traits. Like I mentioned, roles or interfaces. If you're familiar with roles in Perl or Raku, interfaces in Java, it's got some similarities with those types of things. There's a lot of built-in traits to implement basic operators like comparison, debug output, all sorts of stuff. It's really common to derive a bunch of these traits on structs and enums. You can write your own traits, and a really cool thing you can do is you can implement traits that you define on foreign types. So you can define a trait and then implement it on something like the built-in vec or hashmap. And that implementation is only in scope when you import the trait. So you can define a trait in a library, implement it on vecs, and tell users of your library, if you import the trait name, then the vec has this additional method. Otherwise, it doesn't. So it's great because you can extend the built-ins, but you're not doing any sort of global pollution of the namespace of these built-ins. So it's a really powerful feature, lets people write kind of like helper libraries that they can release to crates.io, and using these helpers doesn't like suddenly make a huge mess in every other piece of code that you're using that uses these types. So this is implementing a built-in trait called display. So we can implement it for size, and it just requires that we implement a method named FMT, and it has this particular type signature. It doesn't matter too much the details of the implementation, that's just what it looks like. And then you can call .fmt on a size. And there are also cases where this is called automatically for you, like when you have format strings with those curly braces, it's really calling .fmt on the variable you give it. We can also define our own traits. So we have a trait called reverse. It takes a reference to self and it returns self, so whatever type that self is. And then we can implement reverse for a vec. Again, we can implement our traits for foreign types. And we implement it, we make a new vec, we push a bunch of stuff into it in reverse order, and then we return the new vec. This is very dumb, by the way. This is already built in. There's a reverse method, I think. But I just wanted something really simple. And this is also using generic, so it works for any type in the vec that implements copy. I'll get a little more into some of the generic stuff later. So now our vecs have the reverse method, but only in code where the reverse trait has been imported. And if I run this and I call reverse, it does pretty much what you'd expect. So how about generics? So a good example of generics, we have a hash map that is generic over both the keys and the values. And in this case, the type is inferred because when we call insert, we're passing it to strings. And so the compiler doesn't require us to provide the type, but you can provide the type explicitly. So in this case, we have my struct as the key and a vec of unsigned 64-bit integers as the value. We can say this explicitly. And one thing to note is that this struct that we define can be used as the key as long as it implements the EQ and the hash traits. And we derived both of those. So we didn't actually have to do any implementation. As long as all the structs fields implement those traits, then we can just derive the implementation very simply. We don't have to do any coding of it ourselves. And then we can use a hashmap key, which is really nice. I don't know how many times I've been in Perl and wished, hey, could I use a non-string as a key? It's not every day, but it definitely has happened. So this is a feature I really enjoy. We can also implement our own generics. So this is a collection type, the collection of elements where it can be any type of thing. We derive default, so we can make a default value, and then we can push onto it. And again, we don't need to tell Rust what the type T is in this particular collection, because it infers it by looking at what we pass to push. And that's how we can do generics. We can also constrain the types that we use in generics to have to implement other traits. So this collection version says it only works when the type T implements copy, the copy trait, which is a built-in trait for things that are trivially copyable. So if we try to push a string into this, it's going to complete. And it's going to say the trait-bound string copy is not satisfied. So we said collection only works with things that implement copy. The string built-in type does not implement copy because it's not trivially copyable. Copying a string can use a very large amount of memory. And it says it's required by the bound in this collection. So again, the compiler is always there to help us out when we do dumb things. Another thing that's really great about the type system is there's no nil values. And this gets back to results that I was talking about earlier. So let's say we have something that could return nothing. In that case, we use option. And it's an option. Option is a generic type. It can be an option of anything. So we call our next value method, and either it's going to return none or it's going to return some integer, some unsigned 64-bit integer. And then if we try to write this code like this, where we get next, and it's the result of calling next value, what happens when we try to compare it to 42? Well, it's not an integer, it's an option. So the compiler is going to say, I expected an option, but I found an integer, what the heck? And then it even suggests, oh, maybe you could write it like this. What if it equals sum 42? And that would actually fix it. We could also just do this. We can match against the enum we got back. Option is an enum. Either it's some integer, and we can get the integer in that n variable there, or it's none. And if we do this, the compiler will be happy because we've handled all the cases for option. We didn't try to treat option as an integer or a string or whatever it contains. It just won't let you do that. Similarly, there's also result values. So we're going to try to open a file, and then we're going to try to write to the file. Well, as we all know, opening a file is not guaranteed to work. So we're going to get a similar error, method not found in result of a file in an error, because file variable is not the file, it's the result. And we have to handle that result and extract the file out of it if the open was successful. So the idiomatic way is to write it like this. We're going to write .open, and then we put this question mark at the end, and then again, write also returns a result. We want to check that. We put the question mark at the end, and you'll notice that our open file subroutine here also returns a result. The result is the empty type, and it's an IO result that's either the empty type or an IO error. And then at the end, we return an OK, and that's the OK variant of result. The long version of this looks like this. So if we get rid of those question marks, what the question mark is doing is looking at the value returned by the method or function you called. It has to be a result or an option. If it's it does basically this match. It says, if it's OK, then I'm going to give you the OK value. And if it's an error, I'm just going to return the error as a new result. And so we had a couple of those question marks for the open and then the write, and that's what this looks like. You don't want to write this all out. It's very tedious, and it's just a lot of line noise. All you want to do is kind of pass back the errors and code the happy path, which is generally what you end up doing, and laying something kind of higher up the stack, handle the errors. The question mark version is much easier to read, and this is very common idiom you'll see throughout Rust code. The question mark is the way to do it. Don't do the other. Question mark. No. The question mark is returning the error. Yeah. So like I said, the written out version of the question mark, see it says match file. If it's an error, return error. So yeah, it just kind of handles that for you. So it's kind of a little magical. Rust tends not to have a huge amount of super magical syntax, but I think this was judged so common that it was worth the initial confusion, just because there is so much error handling in code, and wanting to just return the error is just so common. Question in the back? Nope. Okay. All right. Yes. Abigail, and then. So the last double parentheses, there's an OK. You're constructing the OK variant of the result enum, and then the OK contains a value. The value in this case is the empty parentheses, which is like the empty value. It's a little confusing, but often you end up having, If you have a subroutine where you just want to return a result indicating that it failed or succeeded, but the success value, there's no value on success, you're just saying it worked, then you use the empty type. Yeah, the unit type, thank you. Yes. Yep. It does, there's 2 question marks there. So .open has a question mark and .write has a question mark. The first .write, by the way, is just setting an option. We're saying we're making the handle right up. Yes. Yeah, I could have written .open question mark, .write question mark. I just wanted to not make the code too confusing. So we've already seen some pattern matching. We've seen the match operator, but you can also use pattern matching in if-let statements, which is kind of like a shorthand for handling options. You can also do it in while statements very similarly. Inside pattern matching, you can do things like destructuring. So if you're matching an option that contains a point, we can actually extract out the X and Y fields into variables directly in the match. We can also put guards on matches. So we can say, okay, if it's an option that has some point and the X field of the point is greater than 0, otherwise we'll fall through to the next one. If it's less than 0, otherwise if it's none, we'll fall through to that. There's a whole bunch more stuff you can do with the match syntax. I'm not going to go into all of it. I mentioned it has iterators built in. So we have a vec, and then we turn it into an iterator. We can filter, which is like grep in Perl. We can map, which is like map in Perl. Then we collect it back into a vec, and if we print this out, it'll have pulled out just the things that start with D, and it'll print them in lowercase. There's a whole bunch of these list comprehension methods built in. You can also implement our own iterators. So we have a struct sequence, and then we implement iterator. All you have to do is implement this next method. I'm not going to, by the way, I'm going to speed up a little because we're getting close to time. I have a bunch more to cover. So Rust has different types of macros built in. Declarative versus procedural has more to do with how they're, it's both how they're written and how they're used. We've seen some examples of this. Declarative macros use a syntax that's kind of like pattern matching. And then procedural macros are just like code that accepts a token stream and returns the token stream, which is really low level. There's some tools, there's some libraries that you can use to kind of raise it up to a higher level and make it less tedious to work with. We've seen a bunch of macros so far. Everything that ended in an exclamation point, like vec, print line. We also saw the hash mark derive. Those are all macros. So these are some declarative macro examples like vec. The derive is another type of declarative macros. There's also attribute macros. So we could put like a trace macro on a function or an attribute of a struct. And then there's these function-like macros, which is like the SQL example. You just get this stream of tokens from inside that SQL exclamation call, and you do something with it and return something that was valid Rust code. Any language questions so far? All right, cool. I think the rest is simpler. I mentioned there's a lot of good tooling, so there's this thing called rustup. Go to rustup.rs to see the thing to install it. You can just very safely curl something and pipe it to bash. I can't see what could go wrong. I'm sure there's another way to install it, or you could inspect the bash script or however you like. And this will install the latest stable release of Rust, and it'll give you the compiler, the cargo tool, Clippy, and Rust format all together. You can install multiple releases of Rust. You can get like the nightly channel as well. And you can also install other tool chains for cross-compilation. Cross-compilation, in my experience, is not as easy as I would like. It's not as easy as with Go, I will say that. The Go really makes cross-compilation easy. It's harder with Rust, but it is possible. Cargo is the tool you use by far the most. You can run cargo new to start a new project. By default, you're making an executable. If you do --lib, you're making a library. You can do cargo build. You can imagine what that does. Same for test and run. Run is really nice. It lets you treat Rust like a scripting language, which is really handy for development. Cargo has this cargo.toml file. Every crate has one. And this is the example from Precious. You declare some metadata. You put all your dependencies in it, including dev dependencies. And then other tools that work with Cargo. I'm using a tool called Cargo Publish, and you can put configuration for that in there, and then it can read it. There's a really great tool I highly recommend if you're doing any Rust called Cargo Edit. It should be added to the Cargo core tool at some point in the future. It lets you run like add dependencies, remove them, upgrade. It's really, really handy. Highly recommend using this. You can run Clippy via Cargo. Again, Clippy is kind of like Perl Critic. It's just linting beyond what you get with the default compiler warnings. You can enable and disable lints via the config file. You can also do it directly via comments and blocks. So if you want to disable a lint for a particular block, you can do that. Again, it's really just like Perl Critic in that way. And again, things people liked included the ecosystem, the documentation. It's got embedded docs, just like with Perl and Perl doc, although I will say it has Markdown, which I really prefer to Perl doc. And then there's this Rust doc tool that Rust Up installs for you. It generates HTML docs. And when you run Cargo test, it actually will test all your embedded code by default, which is really cool. You can turn that off, of course, with a comment, but by default, it tests it. And then there's an ecosystem around crates. Crates are what we call libraries in Rust, so like a distribution or module in Perl. Crates.io is the kind of one official package repo. You can set up your own if you want. We can compare it to CPAN and pause. And then libdrs is a much better search and display system than crates.io, so I compare it to metacpan. I highly recommend you use lib.rs over searching for things in crates.io. It just gives you more information. And then there's this other site, doc.rs. Everything that gets uploaded to crates.io has docs available on doc.rs, including older versions, all the versions that have been uploaded. Again, a lot like metacpan. It's really, really fantastic. I love it. And then Rust has a really nice community that I've enjoyed participating in. You can find various links at this page on the Rust website. There's web forums, there's some Discord servers, there's a Zolip chat that people use. There's also a really great newsletter called This Week in Rust. You can either subscribe via RSS or subscribe via email. It just collects like blog posts, articles, stuff Rust related, crate of the week, all sorts of stuff. And I find it's a really useful way to learn more about Rust and keep up to date with kind of what's new in the ecosystem. And my experience with the Rust community has been really positive. In particular, I will note that people are really friendly and welcoming, and the kind of bad behavior I see in other communities, unfortunately sometimes including Perl, isn't tolerated. The Rust has had a culture of having a code of conduct and moderation and enforcement of that code of conduct for a very long time. It's kind of baked into every area of the community. And yeah, you just don't. If people kind of start behaving badly, a moderator will generally step in wherever you are and say, hey, please don't do that. And I haven't seen that have to happen a lot because I think everybody knows that this is a thing that happens and kind of self-regulates their own behavior, which is great. All right. Are there any questions? Do you all understand why programmers love Rust now? Why I love Rust? All right. Any questions? All right, well, I will be here the rest of the week if you have any questions, but thank you so much for coming.